Space news is always intriguing, and Friday another first ever reached my inbox. This is the first close-up picture of a star outside our galaxy. Astronomers at the European Southern Observatory's Very Large Telescope Interferometer recently captured this image of a star with a rather exciting name, WOH G64 or WOH, located in the Large Magellanic Cloud over 160,000 light-years away. The star is in the process of dying, ejecting dust and gas before becoming a supernova. You know those neat coincidences where something crosses your path magically while you are reading about something else similar someplace else? This WOH G64 entered my email at the same time I was reading about Sanduleak 69202 in an excerpt from a new book that is waiting for just the right click in my Amazon cart. Sanduleak was the progenitor of the first supernova to become visible to us, naked eye, in 4 centuries. This happened in 1987, and the light and neutrinos from it reached Earth a few hours apart on February 23, 1987. Here it is, or was, a magnitude 12 blue supergiant star located on the outskirts of the Tarantula Nebula. But hang on a second, why did the neutrinos arrive before the light? Were they actually going faster than the speed of light? Neutrinos arrive before light from a supernova because they interact very weakly with matter, allowing them to escape the star's envelope more quickly than photons. Think of a busy mother with a cart full of groceries and a couple of kids running wild around the cart. The kids, the neutrinos, will get to the cashier first because they can escape the process of pushing the cart and interacting with all the groceries. That would be the protons joining with electrons to form neutrons. The remnants of Sanduleak 69202 are now called SN 1987A, the first supernova of that year. These are photos of the expanding ring-shaped remnant and its interaction with its surroundings, seen in X-ray and in visible light. It was the first supernova that modern astronomers were able to study in great detail, and its observations have provided much insight into core collapse supernovae and laid to rest some other theories. This next picture is of 1987A supernova remnant near the center. It's a composite of 2 public domain NASA images taken from the Hubble Space Telescope. So what did we learn? We learned 10 to the power of 57. That is, give or take how many protons join with electrons to form neutrons during the collapse of a massive star's core. With them come equal numbers of neutrinos. During the stellar core's last-ditch attempt to relieve the incredible pressure, a volume the size of the moon will shrink to the size of a city, leaving the outer core at a loss. As the rest of the core tries to collapse inward, even more electrons are thrust into the protons, creating more neutrinos, and the collapse continues. Light, following Einstein's energy mass equivalence, becomes particles and antiparticles, all of which are frantically interacting with each other to shed the intolerable energy. Soon the neutrino numbers have increased tenfold, now 10 to the power of 58, a 1 with 58 zeros after it. Those numbers and the explosion are hard to conceptualize. We also learned that each one of the neutrinos in the 1 to the 58th power neutrino pack has about the same energy as a trillionth of a crashing dinner plate. Individually unimpressive, but collectively beyond imagination. Inside a supernova is 1 trillion years of solar energy yearning to break free from something that is quickly becoming smaller than a city and denser than a mountain per teaspoon. All of this frenzied activity occurs in the blink of an eye. So much is going on that it takes a month of supercomputing time to render just half a second of activity. We also learned that the neutrinos from the Sanduleak event arrived on Earth a few hours before the light from the star did. The Earth was sprayed with 10 trillion quadrillion neutrinos, meaning every person alive in 1987 was dosed with about 1 quadrillion of these energetic subatomic particles. Did it matter? Nope. Nobody even batted an eye. However, as we wait and keep an eye on T Corona Borealis, be sure to set out your neutrino catchers. Greenland is ready. High on Greenland's ice sheet are particle astrophysicists searching for the cosmic accelerators responsible for the universe's most energetic particles. By placing hundreds of radio antennas on the ice surface and dozens of meters below it, they hope to trap elusive particles known as neutrinos at higher energies than ever before. Here's hoping a trillion quadrillion come their and our way soon.